For combat robots with spinning weapons, the more mass one can dedicate, the harder it will typically hit. DES was 1/3 weapon, and Revolve was almost 50% spinning mass, with that weight biased out as wide as possible to maximize inertia. Logically, it would be ideal for 100% of the robot's weight to be dedicated to the spinning weapon to store the most energy possible. It's not an especially new idea. The first of what we now call a Meltybrain might have been Herger or Blade Runner in 2001, with many attempts since. Why Not, used in 2002, had a mechanical translation system instead of complex electronics. Cyclone Bot looks a lot like a modern Meltybrain with its hoop-like frame, and competed in 2003. Jumping much further forward, Band of Team Panic has been working on Meltybrains for the last 5 years with all sorts of designs and technologies, currently competing with Scuffed Single. Project Liftoff is a notably successful design with a large number of wins under its belt from the American beetleweight scene. The objective of this project is to build and compete with a functional 13.6 kilogram Meltybrain at the upcoming Robot Rampage tournament in New Zealand. This robot will be called Tessellate. Unfortunately, it's actually quite a challenge to control a robot that might be spinning at 30 times a second. It usually involves a much higher degree of electrical and software complexity than the average machine I build, so I've enlisted the help of a friend. This is Luke, and we've been working on these robots since high school. He'll explain how they work later on. Now, this video is not going to explain how to program a Meltybrain. Resources will be linked below if one is interested, including the code we're using in Tessellate, but as always, the objective here is to highlight the development process. We're not going to be talking about a wall of code, but a wider mechatronic system with interesting problems and solutions. The first step is to build the machine, of course, which is my department. Briefly, the robot is aesthetically similar to a previous iteration. The welded mild steel frame was designed to be cheap and quick to build, as well as the rest of the robot. Hardox teeth bolt to each end, with 2 belt-driven wheels set on CNC machined blocks towards the middle. 2 large 6374 skateboard motors run at 52 volts for an extremely powerful drivetrain. The laser-cut frame was TIG welded together, parts milled and quickly assembled. Add some wires and the robot responds to basic RC signals and is ready to receive code. Luke will explain how the robot works before following the rest of development.
The grand challenge associated with a Meltybrain is translating while spinning at speed. During rotation, the drive system oscillates at just the right frequency to match the spin of the robot and cause translational drift in a target direction, synchronized so that the wheels are always accelerating the same way. The first problem to solve is reliably keeping track of the ever-changing rotation speed of the robot. Potential methods include precisely measuring the wheel speed or using a beacon system, whereas Tessellate 3 uses an accelerometer. By measuring the centripetal force by the robot's spin, the rate of rotation can be determined with some basic maths. A forwards direction needs to be established and indicated to the driver. Most Meltybrains use a heading LED, which blinks periodically at the same point in the robot's rotation. This allows the driver to orient the robot with intention, and steering is achieved by advancing or delaying the LED blink timing. From here, translational drift is done with a bit of basic logic.
As mentioned, this isn't our first foray into this type of robot. Tessellate 1 competed in Melbourne at the end of 2023. Aside from some technical issues causing premature shutdowns, it demonstrated intentional and controlled movement while spinning at speed. Next was a one-wheel robot of a smaller scale that competed in Wollongong and Adelaide Court Nexus. This machine also worked, but was unstable in its calibration, having to be retuned after every hit when the chassis flexed or the battery shifted. The previous attempt was Tessellate 2, which was designed to use a weighted strain gauge to measure centrifugal force instead of a typical accelerometer. It had a case of spontaneous microcontroller death due to being packed so tightly and never competed. Tessellate 3 will be our largest machine yet, and to ensure it works, we have dialed back the technical complexity to mimic the system of version 1.
The robot's codebase is structured with modularity in mind. For complex problems like the Meltybrains OS, it's helpful to isolate functionality so that each aspect can be easily identified and tested individually. A side benefit is that the main line is written in a human-readable way, making it easy to debug or change the logic of the robot. A single file contains every constant parameter required, particularly those that never change during operation. Hardware constants include which pins connect to motors, LEDs, and receiver channels, as well as essential control parameters such as the accelerometer calibration values. This allows for efficient modification of basic parameters, which then propagate through the rest of the code without having to track down every single instance when a change is needed. Because of these structural decisions, this software is very easily applied to different sizes and form factors of our Meltybrain robots, assuming the same fundamental hardware components.
We'll be starting the development of this robot using an older PCB design. It accommodates the microcontroller and accelerometer, but is too fragile for actual combat. First order of business is designing a new variant that uses JST connectors instead of the temperamental pin headers.
So this is the original plan for the control system for the Meltybrain. It has an ESP32 and a TNC, and the idea was to have them work in unison together. However, for whatever reason, the serial isn't talking, and we're running out of time. And for whatever reason, whether it's noise or whether I've done something incorrectly with the clocking frequencies or whatever, it's not working. And so going back to just using the TNC, which is what we used previously, and we know it works. So we're after a minimum viable product at this point. So this is the redone PCB. Basically, using the schematic, I've generated all the parts into actual component footprints and then laid them out. You have in KiCad, you have like a 3D viewer like this one here, so that you can actually have a look and see how your components are going to be on the final PCB. At this point, we've done all our routing. All the connections on the board are now complete, and so with everything connected up, when you do PCB design this way, the foundations are on basic design rules like spacings between things, what can overlap. And so what you have, once you have completed your design, is a design rule checker. You can see here there's a big list of violations, basically overlapping of different silkscreen elements and most likely distances between different traces. And so this is just a final checker because obviously PCBs are quite complicated. It checks to make sure that you followed the design rules that you set prior to going about laying out all your components. So that's what's next.
For the first time ever, I've actually gone and ordered a PCB from this project sponsor, PCBWay. The parts came well sealed in bubble wrap packaging and ready to have the connectors and headers soldered into place. Luke designed a large amount of silk screening to note the purpose of each connection, which turned out clear and crisp, even using some solder pad as an aesthetic feature for the logo. The PCB itself worked without issue and will be sitting at the heart of Tessellate when it next competes. All combat robots must fail to a safe state when the radio is disconnected, and as a backup, the power switch or link is easily accessible to remove power from the actuators. Obviously, this second option isn't really applicable when the entire robot is spinning at 2000 RPM. To avoid having to try and catch 13 kilograms of spinning steel, the wheels were to not touch the ground until it was extremely certain that the failsafe will operate under any and all conditions. This includes a radio disconnect, the receiver itself failing, or the microcontroller failing.
So what happens when the transmitter turns off is that the receiver outputs 0 pulses. And so what I need to implement is some sort of timer that measures how long it's been since it's last seen a pulse. And that led me to investigate how long it takes for the microseconds counter in the TNT to overflow. And it's about every hour. So basically, we can't have the robot on for longer than an hour because otherwise unexpected things will happen and it might not fail safe.
So we're checking that if this transmitter disconnects from the receiver, it's going to stop all motion, and then we're about to check if the receiver disconnects from the TNC, it's going to stop all motion and not give any power to the wheels. So looking at this value here, which is the mode switch value, currently it's on, and if I disconnect the transmitter, it drops back to under 1,000, and so that's the off state. So if the TNC sees that value be less than 1,000 or equal to 1,000, everything stops. So that's good. Let's do a live test of what happens if it becomes unplugged from the actual receiver, it holds the last value it saw.
It's okay.
It's okay?
Yep. The time since the last packet is going up. So,
this is
it
actually
is very detectable. So
it's
that's
totally
good.
worked. Good job, Luke. You got it before I was even looking for it.
So it's pretty foundational to like the way that it measures pulses, but the system basically checks for any sort of changes. So the signal is like going along like this, right? It detects for any change, and on any change, it will log the current time. And so the way it works is that once it's logged that time when it's seen its last change, if it doesn't see another change on any of the channels within a certain period of time, that causes the fail-safe state, which is why when you unplug it, it goes into fail-safe because it suddenly sees nothing for an extended duration. So
yeah, cool. We have prototype code. We have allegedly functional electronics. It is suspended off the bench. So plug it in for the first time. The step then will be to connect to the VESCs and see if it actually reads what the TNC is sending it. If it is, and it's reading it fast enough, then it's getting the Meltybraining functioning, and then we have a working robot. So we shall turn it on for the first time. This is mostly just to see if it catches fire, but you never know. I think it worked.
it's hard to tell.
Okay.
Is
no light out of the receiver. No, is there meant to be a light on the TNC?
The TNC doesn't have a light currently, so.
The problem. There's two ports that hang on over here. The VESCs are connected to those two pins here. And only one of them is capable of actually supplying 5 volts because we're using the VESC BEC. And it's connected to that one currently.
Motor 1.
But it needs to be connected to that one. So we're going to quickly swap it and everything should be fine. Okie dokie. Pop test, take 2. Oh, there you go, look at that.
We have life!
That's a good sign. Hot tip, don't plug your links in all the way if you're testing things.
And the lights turn on!
They do!
Okay, not all of them, but that's expected, don't worry.
It's expected?
Yeah. We're trying to figure out why the motors aren't spinning or it's not even receiving any signal. And basically, I implemented a safety system so that you had to enable the motors, and then I forgot that you had to enable the motors, and so the motors weren't enabled, and so it wasn't really controlling them. So
Tessellate is using PPM to communicate between the microcontroller and the motor controllers. It is a rather robust protocol, and the equipment can use it to communicate at high enough frequency to switch direction in time. While theoretically well supported, it took a few attempts to get working.
Hook the receiver back in.
So what was the problem? There was an extra layer of protection.
So not only do you need to enable the motors to make sure you really want to run them, you also have to not only set what speed or output you want, but then you need to say, send the output out. And I wasn't doing that, and so we were just sort of setting numbers without actually outputting to the pins.
It's dripping out a bit, but see how it's 2 widths, that's 2 milliseconds, and 1 width is 1 millisecond. So that appears to be working pretty close to what we expect.
Please.
Real time, APM. Oh!
Oh! Yo!
Good job, Luke.
That's so good. That's like all the hard parts until we cut to the next hard part. The control signal working is like, that is kind of huge. Hang on, let's close up this. Oh wow, it's really good at low speed. God damn.
During testing, we encountered a strange issue where the robot would randomly freak out, setting the motors to full throttle and becoming unresponsive to any fail-state conditions. Any issue that affects fail-safe procedure is critical, and hence we immediately began to investigate the cause.
So this is the output that we're getting from the microcontroller. You can see it's reporting a B and an A. So Luke's it prints B at one point in the code, runs a line, then prints A. And so if it stalls while printing a B and not printing A, he can know exactly where in the program that it's causing the issue. Which I think is very smart, because that's how we figured out that it was reading the accelerometer was causing the problem, like that exact command.
Yeah. You also notice that like you're seeing a B at the bottom the most, and what that tells you is that it's stalling on a B the longest out of any of the characters.
Right.
Because otherwise they'd all sort of overlap over each other. But the fact that the B stops occasionally like this, that's when it's reading in the value of the accelerometer and taking time to do that. So
You figured it out.
okay. So basically, with the previous Tessellate, the beta weight one, right at the end, I implemented it's called an interval timer, and what it does is it periodically stops whatever is happening in the program and start running this very specific set of instructions that you need to run periodically. That's all like the melty lock stuff to make sure that the light blinks on occasion. But for whatever reason, using it now, there was an issue where, for whatever reason, it would just like completely halt the program, and then it would like max out all the motors and
like it wouldn't. All the fail safes wouldn't work either.
Yeah, what I ended up doing is removing that whole interval timer thing, and instead just running all those essential processes just in the mainline loop. And we've had it running. You can see here that it's running. We've had it running for probably about almost 10 minutes now, and it seems to be totally fine. And basically, what we assumed was happening is that when it was reading the accelerometer, the interrupt from the interval timer was hitting in the middle of that read, and so the I2C interface freaks out. It doesn't read all the data in, and it freezes.
Because initially we thought it was something to do with like an acceleration spike, because you'd like tap it or shake the robot and it would stop. But it was probably a false positive.
Yeah. There's a lot of interesting things with this issue like that. Like we would tap it and it would turn off and be like, oh, it's supposed to tap in it. And then we would like switch modes and it would error out and we'd be like, oh, it's because you're switching modes. But in reality, it was probably this the whole time, just hitting when we were testing something.
Ollie is joining us. He's been sitting there running the utility for about 20 minutes now, so I think we're pretty happy that it's safe. So take the teeth off, pack everything in there, clear out the garage, and calibrate it. What do you think, Ollie?
Sounds like a good idea.
Yeah, he's got the full explanation. That's what we spent the last 20 minutes doing.
Yeah.
With a technically functional robot, it's spun up on the ground to try and establish a heading lock. It takes a few attempts and bug fixes, but we do eventually get there. Once calibrated, we need to pull the printed data out of the robot to hard code and re-upload, have it saved for the future. Now we hard code that value.
We'll do that first. That's the thing, right? It's always going to do that because as you like move around.
This is a problem. The fact that the center of rotation is not in the middle.
Yeah. That might even be why you're getting that.
And it will be offset towards the accelerometer, which is why we were slowing it down. That's a lot easier to tune.
If you adjust them a little faster?
Yeah. And goes the other way, so I'll bring it back to the middle. It's very consistent. I'll give it that. Alright, get the value out of it.
Values. I'm gonna need your values. Give me your values.
Just want to get away from this one. Okay, so if I go to regular melting mode, which is middle on both.
Yes. Should be.
Yep. Can you grab your laptop?
So the sparks are sick.
It's working as intended.
Forward, you can smell the...
Yeah.
Oh! What is that?
That's so good.
About here is when the new PCB arrived and needed to be installed. Further work is done to improve the robot's movement.
Oh, that's actually real straight. Alright, we're testing it. Bridging over now. Oh. I know what's going on. It's the code. Okay, it's the code now. I swear I can fix this. Okay. So it has angular velocity, which means that this...
Linux. Arch Linux.
Okay. Robot's now working. We just had a small issue where the robot didn't think it was spinning, and that's because the way that it works is it times in between each loop, and if you use an integer data type and you don't manage the data types properly, at some point it will round down to 0 because there's a decimal involved.
And we've got teeth on it now to make sure that the balance isn't causing issues. We're very confident in the fail-safe. We have an environment. Can't hit anything, but we can spin it. While you do that, I'm stopping the pulleys from sliding off because this is meant to be lower and it slowly works its way out. The belt's also getting extremely hot. And I'm hoping it doesn't get too hot because I'm not sure why. Maybe it's got too much tension. The robot is just about approaching a competitive state and needs to be tested at higher speeds. Humans were hidden away behind a wall and up some stairs so the machine could move about. Something happened. I went really fast and the lights went out. So with that hanging issue we're having, where it's not stopping, so thankfully the failsafe still works, we're trying to figure out exactly why. And so Luke is printing basically everything that it's doing, which is I found it very interesting. So if you wouldn't mind explaining what each step is.
So it's got the same thing printed in repeat a couple of times, but if you start from this one here, where it says checking failsafe, that's the start. So first thing it does is checks the failsafe every loop. After doing that, this is right before it changes its behavior based on the control mode. During the translation calculations is mixing the two X and Y directions of the omnidirectional drive together. After that, it's applied to the motors. Then the accelerometer is read, the angular velocity is calculated, a bunch of updating the LEDs and the current robot state, and then the current radius and translation offset. So currently, that is the full main loop of the robot, and so if it starts to hold again, we should be able to plug it in and see exactly where it's holding each loop. So
because it would be fast and then slow down at the step.
Well, you can see the slowest step always ends up being at the bottom, which is reading the accelerometer.
Oh, is that the case?
Yeah, because it prints a block, stops, prints a block, stops, and so the frame that you see is going to be the one that takes the slowest.
Why is reading the accelerometer the slowest?
It's probably just the communication protocol. I2C is slow, and it's probably got I don't know the exact number of bits it needs to read, but however long that takes is probably the slowest part of this whole process.
I do wonder if it's a loose connector.
Alright, it's the accelerometer.
Oh. And what are we going to do about that?
A thing that we can't really do much about. I just poke it with my finger. I don't know. You could put the accelerometer on a higher priority interrupt. That's the only thing that it could be. Is that it's causing things to... I don't know, this makes no sense. Time to look at some endless walls of text.
Yeah, I was going to say, we'll be back when we have a plan. Luke reckons he has a fix for the accelerometer issue already, but we're yet to actually apply it. While it can be difficult to communicate how controllable the robot is, some proof is in the fact that we never hit anything in the garage over a good 10 minutes of translating around off camera. In my opinion, it translates at a good speed and is stable enough through all rotation speeds. Alongside Obliterator, the robot has been painted in preparation to leave for New Zealand, only 5 days away as of writing this. Luke, Oliver and I are going to get packing, so we'll leave on some lights out Melty footage. Until next time.